Section 2.3, Forces and Acceleration. Some important modelling points, and we'll try and add these in as we go through, but during the mechanics course you will get questions that ask about the modelling, and they ask you to make improvements on the modelling, so it's including some of the things that we take out. So all modelling is doing is trying to simplify the situation so that we can perform the formulas and perform the maths. So a particle, dimensions of the object are ignored, the mass is concentrated at a single point. Okay, this means that if you've got something falling, for example, it's not going to spin because we're treating it as a dot. So compared to the rest of the place, or the rest of the dimensions around it, the dimensions of the object that we're working with are so small that we can ignore them, and that eliminates certain things. So air resistance, for example, can be ignored. So if you're asked to make an improvement and it's to do with a particle falling through the air, what improvement can you make? Well, we can talk about needing air resistance if we've been told to ignore it. So it's that sort of thing that you need to be focusing on with the modelling. So, forces and acceleration, we're looking at Newton's second law of motion, which is if a non-zero resultant force is applied to a particle, it will cause it to accelerate. Okay, the resultant force is equal to the mass and the acceleration of a particle. So we're going to be applying that in terms of a formula. We would write it as F equals ma. So up until this point in mechanics, you've only had one set of equations, which has been the SUVAT equations, the constant acceleration formula. The whole of this chapter works on just this one formula. So when we come to do the bigger questions, you've just got to look at it and say, is it a SUVAT or is it an F equals ma? Are we looking at forces and acceleration? And generally the question gives you a hint because it mentions forces if it's an F equals ma question. So looking at example 2.3.1, the forces acting on the body cause it to accelerate as shown. Find the magnitude of the unknown forces P and Q. So when we're doing this, very, very similar to the examples that we were looking at earlier. So example 2.1.3, where we had forces acting horizontally and vertically, and we looked at the resultant force in the x direction and we looked at the resultant force in the y direction. When we're doing F equals ma, F is the resultant force. Okay, so that's what you're looking for. So it's exactly the same as what we've just been practicing. So F is the resultant force in the direction that you're accelerating or that you're working in. Okay, so we've got F is the resultant force, and F and A are vectors, therefore their direction is important, but mass is a scalar, so we don't need to worry about a direction on that. By direction we're talking about pluses and minuses, so just do it by signs. Okay. So looking at this example, if I am to look in the direction of motion, which we can see is to the right because of the acceleration arrow that we've got here, which is pointing towards the right. So that tells me that P has to be bigger than 4, otherwise it couldn't be moving to the right. So just a little bit of thought on that. You can work that out. So working in that direction only, so just looking at the x, the resultant force is P minus 4. Okay. And that is equal to mass times acceleration. Now what I want you to do at this point, even though you know that 5 times 6 is 30, do not write it down. Can you please write F equals ma clearly, put in all your forces in and your multiplications in without trying to do any sort of calculation, because that's where mistakes are made. And I mentioned right at the start of all the videos that in terms of the marking of the mechanics questions, this line is where all the marks are, because they're not testing you on your algebra as such here. So solving an equation, they don't give you much credit for. That's what your core exams for. That's what we're doing when we do pure mathematics. When we're doing mechanics, they want to know, can you apply F equals ma? So even if you can calculate something, I'm going to ask that you just write down F equals ma really clearly, and then on your next line of working, that's when you can do your calculations. So we've got P is equal to 34 newtons. Okay, if we are looking vertically, so we have Q and 5G is acting in the opposite direction. Now, the motion of the particle is to the right. There is no motion vertically, so that means that the resultant force is 0. So what we're working with here is acceleration is equal to 0, therefore mass times acceleration is 0. So vertically we don't have any motion. The other thing just to remind you of is that we've got G, which is equal to 9.8, not 9.81 as it is in some other subjects. Okay, it is two significant figures and it has to be used as 9.8, otherwise you will drop a mark. So we know Q is equal to 5 times 9.8, which is 49 newtons. And please remember that you have to give two significant figures when you're using G as 9.8. So example 2.3.2. So we've got a bus of mass 1,800 kilograms travelling along a straight road, acceleration 3. Just take a moment to try and draw a force diagram. So just pause the video and get a force diagram drawn for this question. When you're drawing your bus, you don't have to be an artist. A rectangle will do. Don't waste time adding all details to it. I like to put the mass into the rectangle of the particle just because it keeps all the information from the question in my diagram, and I like to not have to go back to the question where possible. So we're travelling with an acceleration, so I'm going to draw mine going to the right. So I've got an acceleration of 3. The engine is exerting a force of magnitude of size 6,500 newtons, so that will be going in the direction of motion. So we've got 6,500 newtons going towards the right. By modelling the bus as a particle, find the magnitude of the resistance. So find the size of the resistance. So that's going to be going in the opposite direction because it's resisting the motion. So that will be a mixture of things like air resistance, that friction, anything else that might be trying to slow it down. Now, if we were doing this and putting all the forces on there, we have 2 forces missing. So we would also have our weight acting downwards, and then we always have this reaction, this normal reaction that is perpendicular to the surface that the particle is resting on. So looking at this question, F equals ma. But F is a resultant force, and I'm looking in the direction of motion, the direction of the acceleration that I'm going to use. So in the same way that we looked at earlier, the 6,500 must be the bigger force because that is the direction that I'm moving in, and the X is going in the opposite direction, so because it is opposite it gets a minus sign. So I've got 6,500 take away X, and because I've taken time doing my diagram, I can see that there are no more forces acting in that horizontal direction, so I can move on with the rest of the equation and put ma in there. So then we've got X is equal to 6,500 take away 5,400. And that answers the question. So the magnitude of the resistance it's experiencing is that. Now you might notice at the bottom there is some information by Newton's second law. It follows that a particle of mass m will have weight mg. So this is how you calculate weight. And you just have to think about if you've got a particle and it's free falling, so that's its weight. Its acceleration, if we're going under free fall, will be 9.8, which is g. So it's what we did when we talked about vertical motion in CVATs. So if there's no resistance acting on it and we set up F equals ma, then we have to have the force, the resultant force is nothing else, is equal to mass times acceleration. So that's where it comes from. So to apply it to the question that we've got here, that weight is equal to 1800 G. And then if we're looking in that direction, when we set up F equals ma, there's no motion vertically, so A is equal to 0. So what we end up with here is the resultant force is W minus R is equal to 0. So in this case, R is equal to that weight. And as long as there's no other forces acting vertically, that will be the case, but do be careful because often there are other forces acting. So that normal reaction, the way to think about it, if there's a weight and then you apply an extra force downwards, so you start pushing downwards, then that reaction needs to work harder. So the table needs to keep up the object by applying more force, so it reacts to the situation. In a similar way, if I added a force upwards, then the reaction doesn't need to be as big, it can do less work. Okay, so that's how that reaction's working. So do be careful. It's not a case of reaction is always equal to weight. That's a common misconception on this topic, so do watch out for that. So applying Newton's second law and that weight is equal to mg, let's have a look at this question. So we've got a block of mass 1.5 kilograms, falls vertically from rest and hits the ground at 16.6 meters below after falling for 2 seconds. So focusing on the formulas that we have, so we know F equals ma uses 3 things. It uses forces, it uses mass, it uses acceleration. So as soon as you see all this information in the question, so it falls from rest, it hits the ground 16.6 meters below after falling for 2 seconds, it should be leading you towards the other topic we've done in mechanics. Like I said before, there are 2 sets of equations. There is the force equation, which we're looking at now, and then there's the SUVATs. And as soon as you're talking about time and velocities, you've got to be thinking about the SUVAT equations. Okay. So if we set up our diagram for this, so we have got a block, 1.5 kilograms, and it's falling vertically from rest, and it falls a distance of 16.6 meters, and it falls for 2 seconds. So we've got that information there. Assuming that the air resistance experienced by the block as it falls is constant, so we have got a resistance force, which I'm going to call A for air resistance, and that is constant. Find its magnitude. So we are looking for A. That's the question, and it's always a good idea to highlight what the question is because this has multiple steps and it can be easy to lose your way. The other force that's always there is weight. So applying what we've written up there, we can just put 1.5 G where G is 9.8. So I've got all this information here. I want to find A. So if I use F equals ma and I'm moving downwards, so my resultant force is 1.5 G take away air resistance is equal to mass times acceleration. Now the acceleration here is not 9.8 because when we use it as 9.8 in vertical motion, we're told that the particle is falling freely and we are ignoring air resistance in that situation, so do be careful. So here the acceleration is not known, and you should have worked out that the link between F equals ma and the SUVAT equations, which we're getting as soon as we see time and displacement mentioned, is the acceleration. So that's the link between the two. So I can't find A, so that's what I want. But first I need to find the acceleration, and that's where the rest of the information come into. So sometimes you can't always spot exactly what you need to do in a question, but you've just got to start. And in mechanics, like I say, it comes down to these 2 things on these types of questions. So start writing the F equals ma formula. By doing that, you'll pick up all the marks for writing the formula anyway, even if you don't finish the question. As soon as you see from rest, etc., it's SUVAT equations. If you will write them down, you can build up a solution The problem with these topics is so many people just think, oh well, I don't know where to start, therefore I'm not going to start, and don't make any progress. Everything is going in a downwards direction, so I can keep all of those variables positive because they're all going in the same direction. So we're starting from rest. We don't know the acceleration, that's what I want to find, so I'm looking for that one. So we're using s equals ut plus a half at squared. Remember, these equations are given to you in the formula book. U is 0, it's always nice when U is 0. And then I've got 2 squared. So we've got 16.6 is equal to 2a. So a is 8.3. So that can go up there now. Okay. So going back to that question, just get rid of that so we've room to write. We've got 1.5g minus a is equal to 1.5 times 8.3. So a is equal to 2.25, but because 9.8 has been used, I need to give my answer 2 significant figures. And that is the magnitude of the air resistance.